I'll just make a little recording today, and that is to continue with our lesson on the implicit function theory and corollary. Let's get some practice problems here so we can see what it's like to have to use this to solve a problem. And we already did this one, perhaps, maybe. Given this, which is the unit circle, we showed that an explicit function of y exists at the point 0, 1. That is x equals 0, y equals 1. That's the top point of the unit circle. But it doesn't exist at the point 1, 0. That's the rightmost point of the unit circle. Use the corollary to find dy dx at the point 0, 1. That's the point where it does exist. Okay, the corollary says dy dx is equal to negative partial of f with respect to x over partial of f with respect to y. And that stands for partial derivative of f, partial derivative of f with respect to y, equals this. You see how I get this, right? Negative 2x, that comes from this function right here. I take the derivative of this function with respect to x. I get 2x and I put it there. I take the derivative of this function with respect to y, I get 2y and I put it there. The negative sign, where does that negative sign come from? It comes from algebra. Maybe I should do that now. I don't know if I even have a slide to sort of explain to you where this negative sign comes from. Only 15 minutes left. I'll do it if I have time. Note that the curly D's aren't needed since y is only a function of one variable. You get why I say that? This y is only a function of x. So I don't need to say the partial derivative. It's actually just the derivative. But do you guys see where this answer 0 comes from? If I asked you this question, find dy dx at the point 0, 1, you could answer it. You could say, okay, well, it's negative fx over fy. That's negative 2x over 2y. Plug in x equals 0, y equals 1. I get negative 0 over 1. That's 0. Okay, that's how you would answer that problem. Let's look at a harder problem that isn't so clear and so obvious.
Professor?
Sure.
Can you tell me where the negative comes from?
Yeah, let's do it now. Is it puzzling? Actually, I would love it if it was puzzling. I love to solve puzzles.
I'm looking at it and I can't find it.
Well, okay, so let's start with this equation. F of x, y. Should I do z or just x and y? Just x and y for now, right? Equals 0, even though I could do z. This is how all implicit functions of x and y could be written. Agreed? You agree?
Yes.
Okay, so now let's take the total derivative of f, except it won't be a total derivative. It will be a total differential. And the difference between a derivative and a differential is that a differential doesn't have to be taken with respect to something, whereas a derivative does. If I say the derivative of f, you might say with respect to what? And that's a legitimate question. Whereas a differential does not have a with respect to, because it represents just an incremental change of f in all directions, right? What happens to f? How does f change given all possible movements of all of its variables x and y? So let's look at that. It's pretty much the same concept as the total derivative, though. Let's see what we get. It's going to be split. There's going to be an x channel and a y channel. Just for the same reason for total derivatives, there's an x channel and a y channel. What is it? The x channel will be this, f of x times dx. Okay? The y channel will be f of y dy. Now, this is Jonathan who asked this. You had no way of knowing this, right? This isn't like, oh, you should have known, but you didn't. And the reason you have no way of knowing this is because this is not a derivative. This is what's called a total differential. And the total differential is just like the total derivative, other than it's saying I'm agnostic over what's changing. Like if I said, what's df dx, you could find that, right? Okay, that's how f changes with respect to x. But a total differential is saying, I don't know how x is changing. I don't know how y is changing. But if I just want to know, like there's some change in x, we'll call it dx. And there's some change in y, we'll call it dy. Then the total change in f will be what I've written here on the left side of the equation. And you can even think about the right side of the equation. Well, what happens to 0 as x and y? Some arbitrary change in x and y, it doesn't change at all. It's still 0. So to get from this equation to this equation, all I've done is considered the total differential of both sides. Agreed? And you might ask, well, why is this like this times this plus this times this? It's for exactly the same reason it's true for a total differential. When you have multiple variables affecting, multiple input variables affecting f, you have to sum up their effects. And then this is just kind of due to the chain rule. The reason you multiply them is the same reason that for the chain rule you have to multiply the two terms. Okay? So you can probably see where I'm going. If I asked you to now find dy dx, what would you do? I would subtract fx dx on both sides, and you would get, here's where the negative comes in. Negative, I'm bringing this over to the other side. Negative fx times dx. Now, if I want to divide both sides by dx, this is the trick, right? When you have differentials and if you divide the differentials, you get the derivative. Maybe this is the thing that, I never told you. It's a secret. It's a secret that math instructors have that we don't always tell our students. But if you take differentials like dy and dx and you divide them, you can get derivatives. So if I divide both sides by dx, I get dy dx on this side, and this goes away. This is my version of making something go away. And if I divide both sides by fy, get this on both sides. There you go. This goes away. I should just use the eraser. I have an eraser. Why not use it? There's your answer. What I've derived here is one specific example of the implicit function theorem corollary, using, of course, not derivatives, but differentials, which behave almost exactly the same way, even though they're sort of more arbitrary. They're more agnostic over what actually is changing here with respect to x and y. Well, dx is just some arbitrary small infinitesimal change in x. Same thing with y. Whatever they are, if you divide dy by dx, you're getting the derivative. You're learning how does y change with respect to x. And this formula gives you the answer. It's negative the partial derivative of f with respect to x divided by the partial derivative of f with respect to y. So this, hopefully, even if you don't really understand or care about these differentials, they still tell you something about this. Like, it'll help you remember that, oh, the y goes down there and the x comes down here and the negative is there. Like these are sort of the important things to remember when actually doing these problems, is that the partial derivatives that kind of are flipped and there's a negative sign. But this is where it comes from. Is this at all satisfying, Jonathan? Or is this leave more questions than there were even before you asked?
No, I got it. Thank you.
Yeah. And remember what I said before I showed you this. I said, where does the negative come from? It comes from algebra. What I mean by that is anytime you're moving something from one side of the equation to the other, it becomes negative. That's what I meant. Okay. Let's go back to our problem. Let's see if we have time. We only have 7 minutes. Well, no, that's enough time. I'll at least start showing you the problem, the next problem. Okay. Maybe you can do this for next class if you want. Oh, it's the weekend. Probably not going to make you do it. Okay, question 1. Can we find an explicit function z of x and y in a neighborhood of 1, 1, 1? That's question 1. It's just a yes or no question. Question 2. If so, please, should have said please find the partial derivative dz dx at 1, 1, 1. You think we could do this? Maybe not in 5 minutes. We only have 5 minutes. Want to do it next class? How's everyone feeling now? Want to do it now? Want to do it next class?
I do it next class.
Okay, that's fine. I mean, you could look at it if you want in between now and then, but I'm fine waiting. And just as a preview, to answer question 1, what are you going to use? The implicit function theorem. You're going to see, oh, let's call this f. I need the partial of f with respect to z to not be equal to 0 at this point. That's what question 1, that's what I need for question 1. For question 2, find the partial derivative of dx. Well, that is simply, remember the flipping, those red arrows where I flipped? It's going to be negative. I'm basically giving you the answer here. It's going to be negative f. Remember, I flip it, so x is on the top now, and z is on the bottom. That's going to be the answer. Right? But evaluate it at 1, 1, 1. And for this one, we just need to show that f z not equal to 0. So I gave you the answers how to answer the questions. I didn't actually answer it, but we'll do that next class. Okay. Hope you guys are feeling good about the class so far. I tried to give you this news about if you do better on the final than the midterm, it'll help your grade. Just so you have more hope and about, still try to get a good grade in this class, because I think anybody have any questions? I feel like we can let you go 4 minutes early today.
Yeah, so Professor, so assuming that you do worse on the final with that also, would you be able to rearrange the grades for that?
Oh, you mean,
so say that you did good on the midterm and then you do worse on the final.
You want me to bump up the percent of your midterm? No, yeah. I don't want to do that. I think the final is bigger than the midterm, actually. The final is somehow more important. It will focus on the second half of the class, but remember, the second half builds on the first. So okay. If anything, I think the final is a better, what's the word? Representation of your overall understanding of the material. So I actually don't want to do that. Maybe I'll find some other way to reward people who did very well in the midterm, because you are rewarded because it's 30% of your grade, right? It's good that you did well on the midterm. If I'm not saying you did, but if you're a person who did well in the midterm, you still be directly rewarded in the sense that it helps your grade. But maybe I can think of something else where I don't want you to, because let's say I said okay to what you just said, then it really takes away your incentive for doing well in the final, because you have the midterm to fall back on. And in fact, even learning the material in the first place, some of the incentive goes away, because whatever exam you'll have to take about it is going to be discounted, and you've sort of got the grade you want locked up. I do want to reward you for doing well, but I just don't want to take away your incentive to learn the material, the rest of the material. There's the half of the class still left to go. I think it'd be bad if I did that. So we can talk about some other ways to reward you.
All right, sounds good.
Okay. Okay, guys. I'll see you Tuesday.
All right. Thank you.
All right. Have a good weekend.